So it's my pleasure to introduce our first speaker for the afternoon, Matt Hedden from Michigan State University will tell us about, sorry, I lost the title here. Rational slice genus bounds from not Floer homology.
Yeah, I think that's right. I was trying to remember myself, and it's something like that. So yeah, thanks a lot, Chris, for the introduction and the invitation, and for organizing. It's really a pleasure to be in Miami again after many years. So yeah, so I'll talk about rational slice genus bounds from not Floer homology. So it's a pleasure to talk about the project. This is a joint work with Katherine Raoux. And so ultimately, the goal of this talk for me is to advertise to you kind of a new minimal genus problem for surfaces or for knots and three manifolds relative to four manifolds. But if I were to just define it for you right now, I think it might seem a little unmotivated. And so I'm going to take a trip through history, my history, and tell you through kind of some of the ideas that gave rise to this for me. And then maybe at the end, I'll talk about how what we're dealing with in this talk connects to what Jim is discussing before lunch. So I want to just start with this definition of a simple knot in a lens space. It's not as where much of my motivation initially comes from. So if you look at the standard genus 1 Hagar diagram for lens space, minimally intersecting, so here I'm going to draw or attempt to draw L5-2 with respect to some convention. So for those familiar with Hagar homology, or probably even not, you can specify a knot by putting two pairs of base points, or putting a pair of base points on a Hagar diagram. And the convention then is that I'm going to form a knot by connecting the pair of base points from D to W by an arc that doesn't intersect the alpha curve. And then I'll connect W back to Z by an arc that doesn't intersect the blue curve. Okay, and then the convention is that the arc and the complement of the alphas maybe lives over or under, depending on your convention. So if you have a lens space, then you have maybe P-1 or P knots that you can form this way because of the number of complementary regions. And I'll call a knot form this in this way a simple knot. Okay, so this is, I mean, they are fairly simple looking class. There's not that many of them. And so kind of the motivation for this comes from construction and conjecture, Berge conjecture, says that if K is a knot in the three sphere, on which integral surgery, the surgery yields the lens space necessarily LP in some Q, then the core of the of the filling torus is a simple knot. So motivation was this, Bernie had this construction, he took knots in three sphere, which were doubly primitive with respect to the standard genus 2 Hagar splitting in the three sphere. And then he observed that if you do surface framed vein surgery, Hagar surface framed vein surgery on such a K, that you get a lid space. But then if you look at the core, where the core of that filling torus goes, it goes toward these knots. So dually, you can think about this as a conjecture about the knots and lid spaces on which you could do surgery to get the free sphere. So the Berge conjecture, which is a complete classification of the exceptional surgeries on knots in three sphere that give lid spaces, it's really about this class of knots. And so I got interested in this. Observe that a simple knot have simple Floer homology. So that's to say that that the Floer homology, as an unweighted vector space in such a knot, is isomorphic to the Floer homology of the underlying lid space. And the rank of these groups, both B. And so, so I proved a theorem in Jake Rasmussen, that alternative perspective and proof of this, says that in fact, if surgery on K in a three sphere yields a lid space, then the knot Floer homology is simple. So the knot Floer homology is isomorphic to that of one of these plots. Oh. This is for the dual knot. So from the perspective of Hagar homology, then the dual knot looks like that of one of these Milky knots. And so this was my motivation to go after this was this conjecture that Kim Baker, L.A. Grigsby, and I proposed that if HFK of a knot in open space the same as triple knot, then this should imply that K is simple. And the motivation for this conjecture is, well, there's some sense in which this Floer homology is so simple. I mean, it's all it can be. And if you think about like the lid space L11 in the three sphere, there's a unique knot that has Floer homology on that. So this is minimal rank, at least for the three sphere tells you that that you're uniquely specified. So this is some kind of Botany type conjecture, and this conjecture implies Berge conjecture. Okay, so that but so the question is, why would these knots be unique? I mean, what's special about them? In what sense could you make the case that they're likely unknown? And is characterized by the knot Floer homology. Nowadays, we have a lot of results about knots that have been characterized by knot. I think it's another like this, so maybe we can still retain for this. But Jake proposed that that there's that the reason that they might be specified by the Floer homology has to do with a minimal genus problem in the lid space. So let me define the notion of a rational surface. So, given the three-manifold Y, I guess I need the knot to be 0 in the first homology with rational coefficient. So I'll say it's rationally homologous. Then a surface which is smoothly mapped to phi, which is embedding away from its boundary. And on the boundary, this map is a people covering. Okay, so K is not infinitely homologous or rationally homologous, then we know that some multiple of its homology class is 0, and so then that would be a sufficient key for this to have the same surface. And we can define no, sigma doesn't have to be connected. No. We can define a Q genus, a Q Seifert genus. So this is going to be, this was I think, this is one of the, I first saw this definition in the paper of Calegari and Gordon, were motivated by these types of issues. So you can define, and they denoted this, I believe, by K. Y. So I have not a Q manifold. This is going to be the edema of negative Euler characteristic of sigma over 2p, where sigma, so this is the edema over all sigma, where these are Q Seifert surfaces. So I look at that, and so I notice I'm dividing by the order of that power right now. Okay, and so in these terms, then Jake made the following conjecture. Floer simple knots minimize genus and minimize the rational genus in their homology class. So that means if I have any other knot in the same homology class as K, that that it's going to have this quantity no smaller than in K, if K is simple, and moreover. And this is the key point. This is why this would imply the Bergian conjecture. They are the unique minimizers. Okay, so so we have a theorem to this effect. So Jake proved that Berge dual knots minimize genus in their homology class. So this was kind of what motivated him. And more generally, he proved that a Floer simple knot minimizes genus in its homology class if its rational genus is less than or equal to half. And then later, Ni and Wu showed that in fact all Floer simple knots minimize genus in their homology class. So independent of what the rational genus of such a knot is. So unfortunately, in terms of this conjecture, the unique minimizer, this hope that simple knots, Floer simple knots are somehow like the knot in the three sphere. That turns out to be false. This was a theorem of Green and Ni. The conjecture about uniqueness is false. In general. So there are these Floer simple knots out there, and there are some other knots that have the same rational genus in their homology class, and the construction is through certain Gables. But it might be true. So all of their examples have kind of large rational genus. So it still may be true for Floer simple knots with rational genus less than a half. And this is the class in which the Berge knots or the Berge dual knot sits. So this would, if you could prove it there, you prove the Berge conjecture.
So rational takes explicit description of this Berge.
So yeah, actually, so the point is that if what he showed is that if you have a Floer simple knot with small enough genus, then the structure of the knot homology combined with the surgery formula, tell you what the suppose. Okay, so it really goes. If you have a knot in a Lin space and you have a L space homology sphere surgery, then you can use the surgery formula to conclude that that the knot is Floer simple and that it also has small rational genus. And then he uses a divisibility theorem for the Euler characteristic of knot Floer homology and rational homology spheres due to divisibility for Reidemeister torsion due to Brody in the 60s to conclude that they're actually that they minimize genus in their homology class. Okay, so the status in this I don't quite know, but kind of my motivation then, I'd like to understand this class, the Floer simple knot better. I think it's a very interesting class. We don't understand it nearly as well as we could. So there are other, outside of these spaces, there's lots of Floer simple knots known. So we have inside the branch double cover of alternating knots. So these are well known to be L spaces. They're strong L spaces, and they contain lots of Floer simple knots. I'm not sure whether they contain Floer simple knots in every homology class or not. You can think about Floer simple knots that might not live in rational homology spheres even. And so instances of these, you can look at the F1 fibers in high degree circle bundles. Over sigma G. Another place where they naturally arise is they arrive at the dual knots to L space surgeries. I don't know. You can think about what it means to be a Floer simple knot in a manifold that might have non-trivial. That might not be an L space. So that would just be a knot that has the same knot Floer homology as the underlying three manifolds HFF. So that's a concept that makes sense. There are just a handful of examples that I know of. But if you think about Jim's talk last time, if there were not that realize this is the way model these would be put simple. In some example, just what homology would rank an homology sphere. Okay, so I don't know what the classification is, but I'd like to establish that so we should understand it better. So we'll understand for simple knots better. So hopefully, maybe classification is too much, but what makes them special? From maybe a geometric perspective, and hopefully, special enough to say that they're uniquely characterized by some of these important conjectures. Okay, so today I want to, there's a number of other kind of geometric aspects of these sort of simple knots you can consider. So many of them are fibered. So in particular, the Brugge dual knots are fibered. And due to that vibration structure, you can put a contact structure on the knots. So there's naturally associated contact structures for simple knots in these situations. And maybe you could hope that these contact structures will aid in their characterization. So this is something that I spent some time thinking about with Olga on the outside. And I think you can combine that and talk about geometry and categories That's not exactly what today, so it's not what I was mentioning. Yeah. 3 questions. Is this about ratings? There are ratings here, and so I'll make the, I guess, stronger. I don't know whether it's stronger or not. I'll make whatever conjecture you like. You can interpret it in all ways. I'll make all those conjectures. For equal knots, what is the genus minimizer? Well, it's the Brugge dual. No. What's the genus? Oh, the genus. It's the genus of the knot in the free sphere. I mean, it's the genus of the knot in the free sphere. I mean, the complement of the Brugge dual knot has the same complement as the knot that you can circulate on the free sphere. In general, it's a kind of a complicated recursive formula. You have a homology class, you can represent it as a number k. So there's PQ and K. PQ parameterized the lens space, K parameterized the homology class, and there's a recursive formula to compute the genus of the simple knot in homology class K. It's somehow the same formula for computing the Euler characteristic, not for homology of that knot. But I don't have a great description of it's a weird formula. It's not a particularly smooth surface, simple surface. Oh yeah, no, it's not. I mean, they're very interesting surfaces. I mean, but they do have this property, at least the Brugge dual knot, that they have this rational genus is still small. The genus of the surfaces is growing large, but the point is that the order of the homology classes is also growing large enough so that when you divide by it, it stays small. Oh, and maybe I should say, yeah, there's a really nice result of Ken Baker. And Ken's not in the audience. I was hoping he'd be here so that he could correct me all the things I'm probably, They're not planar. No, they're, I mean, take the 7597 torus knot, that has some big genus, and that surface exists in the corresponding lens space, and it's the minimizer for the Brugge dual knot for the 2 lens space surgeries. Yeah. So I should say though that if you put an additional that the rational genus gets really small, then in fact you do have that there's unique minimizers. So the result of that effect is the genus is really like 1 over 406, or something like that, and Calegari and Gordon's paper. But there's also a really nice result from Ken Baker's thesis that says, and I can't remember in these terms what the constant is, but it's the rational genus of a knot in lens space is small enough, then it is a simple knot. So he proves the Berge conjecture for certain homology classes and things.
Okay, but I want to talk today about four-dimensional aspects of this story. And so, well, what I'll do is I'll just think about the, kind of four-dimensional analogs. So I'll replace a Q Seifert surface by a Q slice surface. And so here, it's going to thicken up sigma is y cross I. So this is a kind of the only universal format that y arises that's boundary. And similarly, I'll talk about the Q slice genus. Again, thickening up this quantity. Now to note this Q slice genus by y cross I. And so, so Katherine and I, I've been kind of interested in this class of knots for a while, and Katherine and I have been working on some relative adjunction inequalities for non-Floer homology that can tell you about the genera of properly embedded surfaces, smooth and properly embedded surfaces, and smooth Floer manifolds with boundary. And so we have this this result about certain genus bounds that take as input a numerical invariant, a tau alpha. Okay, so given your favorite Floer homology class and your favorite tree manifold, it doesn't have to be your favorite. You look at the minimum over the Alexander grading. So not Floer homology comes equipped with an Alexander grading. You look at the minimal Alexander grading of any cycle X whose homology class equals your favorite class alpha. So this is the minimum overall X such that X equals the homology class equals alpha. So this is some, in general, this is a rational number. For a null homologous, traditionally null homologous to be an integer. For a rational homologous knot, the Alexander grading takes rational values. Okay. And so we have this relative adjunction inequality. We had in our hands. It says that, so if you have some cobordism, smooth cobordism W from Y1 to Y2, and the associated map on Floer homology sends a class alpha in the Floer homology of Y1 to a class eta in the Floer homology Y2, then we get adjunction type inequality. And so that's this relative invariant, or this cobordism invariant comes equipped with the spin C structure. And I have this isn't beta, this is eta. What is capital A again? This is the Alexander grading. So we have this inequality for all smooth and properly embedded surfaces. And W, whose boundary are your favorite knots, K1 and K2. And really, there's talking about oriented cobordism, so you should think about the negative K1. Okay, so we have this inequality, and this is and we're thinking to ourselves that what better Floer manifold to apply this inequality to than y cross I. Because this is the identity in the cobordism category, if you like. And so So the map on Floer homology is that identity. And so, everything's in the identity. So this is, is non-trivial map that you can get on a Floer homology between the Floer homology and the boundary. So you're going to get the most in terms of the genus bound, the best genus bounds for this manifold, which of course makes sense, right? Because yeah, it makes sense. Everything. Okay. So our hope is like, oh, we're just going to use this. We're going to use this fact, and all the time they're going to give us genus bounds for these simple bounds. So hope is that all time invariants give Q genus bounds, Q slice genus bounds. And so there's this caveat, well, these bounds aren't homologous, so they don't bound anything like last time. Thinking why is not going to make something bound that didn't bound before if you have a gene that's homologic. So we said, well, just take a table, blah, 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 compare, stuff. And then, we would hope that this would be what happens. But something really interesting, and at least, when I first thought about it, I should have seen something that I missed. Well, update or something. So, so one thing to note is that in the case of traditional like these flavors, let me actually I'll say it right now. So the case of snag here is like let's look at what happens when you consider the intersection of a Q Seifert surface. Let's intersect a Q Seifert surface with a neighborhood inside of Y of a knot. So this is some tubular neighborhood of knot, it's a solid forest, and the surface, because of the condition that it's embedded away from K, covering on K, what we see is that this is really a cone on a cable of K living in the boundary of this tubular neighborhood. So this is it. So it's some knot living on the torus boundary of the tubular neighborhood. And what the intersection of that rational Seifert surface with that neighborhood is just a cone on that knot, on that torus knot. So there's a cone on a cable. And this isn't just any cable, this is a specific cable. And the specific cable is determined by so this knot K is non-homologous in general, so it has a linking. The linking form of the manifold applied to its homology class, some Q minus Z value number, and that what the Q is here is determined by that linking form. And strictly speaking, maybe you see some parallel copies of the table. But the point is that the Thurston norm, which is essentially, so what we're doing really is we're looking at the genus of this null homologous table, or the Thurston norm of this table. And since the Thurston norm is linear on rays, it doesn't matter if I took some multiple of the homology class of that Seifert surface with the cable. So that's what happens for a Q Seifert surface. So really, the new genus problem for in 3 dimensions is just about the Thurston norm. No different than studying the Thurston norm. But the situation is not different in 4 dimensions because if I do the same thing, give us the properly embedded surface, now I'm like that. And this is now a cone, no longer on a cable, but on a knot, which is living inside of. So what does this tubular neighborhood look like? It looks like a solid torus again, across some small interval up near the boundary. So this is now a cone on some knot in a solid torus, in a nearby solid torus to the solid torus neighborhood of K inside the 3 manifold. And it projects
onto the core of that solid torus is the covering element. So this is a closed braid. It's living in some braid group, BP. And that P is some multiple of the order of the non-homology class. So is it clear what's going on here? I've lost complete control of the, here I have a three-dimensional column and I was just considering the Thurston normal as specific knot. The genus is specific knot. Here, I'm trying to minimize over all national flight surfaces. And so this kind of discussion tells us that the rational slice genus of a knot is really a triple infimum. The infimum over all P that are multiples of the order of the homology class of K. It's the infimum over all braids in the P-stranded braid group. And it's the infimum over all surfaces of negative the Euler characteristic of the surface over 2p, where sigma is a smooth embedding of a surface into y cross I, whose boundary maps to what I'll denote by beta k. So beta k is a satellite knot of k. So a satellite knot of K, you have to look at the tubular derivative of K, you have some knot embedded in that solid torus. And here I'm embedding a closure of a braid beta. So this is some kind of like multi-parameter, minimal genus problem that we have to solve. Maybe I shouldn't erase this. And the reason I don't erase it is because I had hoped that all these tau alphas were going to give a bound for this quantity. For this quantity, but what those tau alphas bound, so they only apply to give bounds for knots and three manifolds that bound surfaces in the four manifolds. So I have to apply, so I can bound the genus of these surfaces bounded by multiples of K. And so, so the issue, if I look at any one, I can find pattern knots, braided pattern knots. So I have this solid torus, and I'm going to embed in this some p-stranded braid. And so because I don't have any control of what that braid is, I know that I can find braided pattern knots beta such that tau alpha of beta, that braided pattern knot applied as a satellite operator to K, is more or less arbitrary. And so if you've thought about cable knot before, the issue is so I can look at like the P, Pn plus 1 Gables, and I can vary parameter n and see how does the tau invariant of the cable of K look as I vary n. And so if I consider a single tau invariant, what happens is I'll consider the absolute value because that's the thing that should be bound in the genus. What happens is that, as n goes off to infinity, you're looking at
you get this big torus knot, P plus one torus knot that's living in the solid torus, and so that's sort of dominating the issue at hand. And so the genus of that torus knot that's living in the solid torus is going to start to show up in the tau invariants. And so as you go to positive infinity, the tau invariants are unbounded. And then as you go to negative infinity, the tau invariants become arbitrarily negative. And somewhere there's sort of a sea change where where the tau invariant for a given class alpha is minimized and actually I guess if I'm looking at the value, I was anything under there. So it looks something like this. So that's what the graph looks like. And so you sort of abandon homology because you think, well, there's no way to really control these tau invariants. But then, you just keep going. And you say, well, maybe we can prove, like we can understand really well how the tau invariants of just a specific class of braided patterns, cables behave, and then maybe I can use this to say something about arbitrary braided satellite paths. So I guess, and this is where, for those of you who know me for a long time, you know that in graduate school, I developed a Pavilion cabinet. And so I've been struggling with this for a while. But well, for those who don't know me, well, now you know. And so I think it's going to be a long wagon, and so here's our visual result. So if K is a knot in Y, then it's rational homologous. And beta is any braid in the p-stranded braid group. Then for any alpha, so for any non-trivial class, we have this inequality. So we have so we look at this satellite. Okay, with pattern beta. So this is the satellite pattern, the closure of beta inside the solid torus. And we want to compare that. So the intuition is that you're multiplying, you take a p-stranded braid, so you're basically like multiplying that knot by a few times. And if you think about the natural surfaces you might construct, you would expect then that the surfaces, the Euler characteristic would multiply by p, and hence the tau invariant might also behave similarly. So indeed, there's some sense in which you're multiplying the tau invariant by p. But then you would also expect to see something that depends on the gradient question. So here's this divide of the gradient. So you would expect then that the more positive the divide, the higher the genus and the higher the tau invariance. And so that's saying that as you get very, very highly lived braids, tau of the braided satellite is going to look like p times tau of the knot plus the ride. Then I also have this direction. Notice that when you form a satellite, you have to identify that tubular neighborhood of the knot with a solid torus. This identification is done with a random, which we can think about as a curve lambda. And so I have this additional term here, which is P times P minus 1 times the linking of K with lambda. So in general, in rational homology space, the linking between two curves is going to be a rational number. And so I consider the linking of the knot K with its parallel push-off as defined by the gradient that you chose to identify its neighborhood with the solid numbers. So the claim is that these are almost the same, and they stick on the distance, P minus 1. And I guess there's also a much better, this really applies to all braided patterns, so beta might have closure, which is a link. Okay, so that's the result. One thing I want to observe is that, this should be a positive. So one thing to note is that this quantity here is independent of the framing. So your framings are not exactly with integers, you can flip them on the meridian. If you vary the framing that you're using by 1, this linking number goes up by 1, so you get a corresponding additional factor here. But then, adding a full twist adds a full twist to that braid, so that makes the line go up, and so there's a corresponding negative. So this is independent of what framing you use. It's kind of convenient packaging.
Are there any questions about the statement?
Okay, so this kind of issue that we ran up against, that we don't really know what's the best, what are the best boundary conditions for our minimal genus problem that we're trying to solve, and we're able to bypass this because in a general 3 manifold we might have lots of Floer homology classes. In the 3 sphere we have 1, so you just have 1 tau invariant. There's not much we could do. But for a general 3 manifold, we can make the following definitions. Say tau max of K is equal to the maximum over all Floer homology classes of tau alpha, and similarly tau min. And so the corollary that's what saves us here of this theorem is that tau max of K minus tau min of K, despite this being, this is just K. This is a single, we compute the homology of K. We look at the maximum taus, and so we just get this quantity. Despite the fact that we really had to compare it, that quantity to all of the braided satellites of K, and we do get the type of bound we want. So this is a rational slice matrix bound. And so the corollary was what we set out to prove initially, is that Floer simple knots. This shouldn't be obvious. I mean, this corollary. Yeah, I mean, it's a corollary, but it's not it's kind of I'll give you a little bit of intuition for it in a moment. I won't prove it because the proof would involve a bunch of just strings of symbols and stuff. But I'll tell you the idea that sort of made this work. So Floer simple knots have their Floer genus equal to their 3 genus. And so this corollary of this corollary, this one should be clear, because what is this? The 3 genus is supposed to be, according to the fact that non-Floer homology detects genus or Thurston norm, this is the difference between the maximum and minimum A ratings of any non-trivial non-Floer homology classes. So this is the breadth of non-Floer homology. And now, so what's the difference? So on the other hand, we also know now that if you have some non-trivial non-Floer homology classes, because it's Floer simple, those non-Floer homology classes have to give rise to non-trivial Floer homology classes in the ambient free manifold. There's no more non-Floer homology than there was Floer homology of Y. And so this quantity, this tau max minus tau min is equal to A max minus A min. This uses Floer simple because there's just no more Floer homology there, not Floer homology there. And so combining these two, then we see that these Y symbols are K. Some of my Y symbols are K, yeah. Thanks. Okay. Let me come back to your question. So the idea is this picture that I'm erasing now that sort of tells you about the behavior of one tau here. And say, let's just think about, again, let's think just about the case of PPN plus one cases. So this is, it's not all braided down like it's pretty good. So if I have like tau alpha, I have this graph that looks something like this. This is absolute value of tau alpha of KP plus one. And what this theorem tells us is that we're sort of bounded distance. We're in this kind of red tubular neighborhood of width P minus one. So that's where this error term is. So this is this quantity is like P times tau of the knot, P times tau alpha of the knot K. So now we take another Floer homology class. And so so maybe I have another Floer homology class beta, and tau beta is much less. So tau beta is much less when you have positive in, but as you the fact that it is smoothing out when you're making n get large, when the rise of these braids is getting very, very big. Well, that's okay because eventually we're going to vary over all braids. Or in this case, just all ppn plus one cables. And so once it gets, it's going to go into the negative zone sooner, and so its absolute value is going to start becoming positive sooner. And so now the question is, we just want to know that somehow there's enough spread between these two that at some point it's always going to have a tau that's fitting out. So that's the kind of intuition behind this, behind the corollary. The intuition behind the theorem is, we actually proved it on our tables. And this has this thing that I've been using throughout my life. It's a very nice Hager diagram for tables that you have a Hager diagram which is simultaneously a diagram for the knot and the table. And so you can relate the Floer complex in a very nice way. And so that's if you look at cables, so a special Hager diagram, and then you relate the tau variance of cables the tau braids, or braided satellites.
by Gaussian chain inequalities that hold for these generalized boundary. Okay, so I just want to conclude observation that this difference, this tau max minus tau min, is invariant under a connect summing with local knots, with knots in the three sphere. So in particular, genus bounds really aren't genus bounds not just for so this rational slice genus. So this is really a bound for the PL rational slice genus. That sort of analogous to what Jen and Matt and Hugo are considering. So if you have an invariant quantity which is invariant on the connect sum with local knots, then you can sort of trace through the arguments she gave us to see that this is actually an invariant of PL concordance. If it bounds the genus, it bounds this quantity as well. And so maybe it's a further corollary. If K and Y is Q null homologous, and beta is a p-stranded ring, then P times tau max of K minus tau min of K minus 1 plus 1 is less than or equal to tau max of the braided satellite of K. So this doesn't matter. It doesn't matter whether K is no homologous or rational no homologous. I mean, no homologous works just fine. So this is the consequence of these inequalities appropriately written down. And so then this tells us that if you have a knot in a three-manifold, even say an integer homology three-sphere, for which the difference between tau max and tau min is strictly bigger than 1, then if you take p-stranded if you take p-braided satellites of that knot, then the tau max minus tau min of those braided satellites is going to get arbitrarily large with the braid index p. And so that's going to tell you in turn with this genus bound that the PL genus inside Y cross I is going to get arbitrarily large. So I mean, in some sense, this is very similar to what they've been doing. They were also taking cables. And I think that this result then proved that the genus of surfaces in their four manifold has PL genus arbitrarily large. But what we don't prove with this is we don't prove that there may be another homology four ball that their manifold bounds, and they're showing that actually the PL genus is bounded in that four manifold as well. And this technique really can't handle that. So it'd be interesting to see sort of further applications. And I'll stop there.